Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is going to look at the n queens problem, otherwise known as the 8 queens problem, using the C++ programming language. So what does that exactly mean? What is the n queens problem? So let's just start simple and just say, if you need to understand the game of chess, go ahead and look up chess rules. We're going to keep to just what a queen does. There's no strategy involved with this. This is just a matter of, just solving a specific problem. So let's just presume we have a 4x4 chessboard, just to get the simple case out of the way here, and say a queen in chess, if I put a queen down here, the queen can attack in any direction in any number of squares. So that would mean that I could put a queen here. If I put a queen here, stupid. Let me see if I can fix this up here real quick here. And of course I can't. Format cells and make this text just so I don't get all this nonsense here. Okay, so if queen is there, let's just put X's here. Whatever, I didn't need to do any of that. So the queen can attack any horizontally, vertically, or diagonally, any direction, right? So all of those squares are taken away from us if I wanted to try to put down n queens on the board so that none of the queens are attacking each other. That's the end goal here. So if I put a queen here, oh my goodness, right, that ruins a lot of stuff. And you can maybe see here that I cannot do this if I put a queen here, because that would require me to put a queen here and a queen here. Because you would think I have to put one in every column and every row, and then none of them can meet diagonally. So if I had to put a queen here, that would kill this one off. And I can't put another queen here because then they would attack each other. And that's the only place, with this queen the way it is, that's the only place it could go. So it's just a matter of placing ones on the board. So I'm like, well, if I put one here, okay, I'm not going to write everything out. So if I put one here, I could either put one in here or here, right? Either this space or this space. And again, since we can only put one per column, so we just go with it, right? So let's see. If that's the case, and I put one here, then my only two options are here or here, and I can't do that because then they would attack each other. And so this is out. And so I could try this one. And so I could say, okay, so this is the only option that we know of right now. We're actually recursively going through this and solving the problem. They say, I can't put these two options, I can't put it here, but I could put it here. We're like, okay, so then the only thing left would be to put that there, and we can't put it there because that doesn't work out. So, okay, so far, what we've worked our way back to is that this square cannot hold a queen. So we don't even know if any square can hold a queen, but what if I put one here? And so now this is out, this is out, this is out. This has to be the only one that can work. And so now of these two, this one doesn't work, so this one works. And then of this one, we can put one here. So let's see, nothing diagonal, nothing diagonal, nothing vertical or horizontal, nothing horizontal or vertical or diagonal, nothing diagonal, horizontal or vertical. So this is an actual solution to the 4x4 case. And so depending on how you think of it, I'm just going to say, like, if this is 0 and 1 and 2 and 3, why is some of them centered and some of them not? I don't know, whatever. And so what I can say here is if this was a vector, if I had a vector of queens or a vector of integers, I could say that the first queen was at position 1 in, so let's say the element number itself is the column number. So element 0 would be a 1, column 0 would be a 1, column 1 would be a 3, and then there'd be a 2, and then there would be a 4. So 1, 3, 2, 4 could be a possible solution. Or if you want to think of it, I'm sorry, maybe make it 0 based. So 1, 3, 0. I don't know where the 2 came from. Sorry. 1, 1, 3, 0, 2. I have no idea. Whatever. This is my 4th take, and I'm not doing it over again. So anyway, so 1, 3, 0, 2. 1, 3, 0, 2, and that's how I would set up my vector, and that's how I would print things out. So running this code with the 4x4 case, there are only 2 possible solutions, and you see that 1, 3, 0, 2 and 2, 0, 3, 1, which is basically just a mirror image copy of what you already see. Just you flip the things over. This 1 becomes 2, 3 becomes 0, 0 becomes 3, and 2 becomes 1. So so we like to say that's truly not a unique solution. There's only one unique solution, because if I can mirror image something to get to another to get the same confirmation, it's not truly a unique solution. If I can rotate or whatever I can do to make it work, it doesn't work that way. So, but the key is I could have chosen, like we started out here, I could have chosen 4 for each of these positions, 4 times 4 times 4 times 4. So that's 16 times 256 different possible ways that I could do this. And if I brute force this, I could try all 256 methods and figure out which ones of them just to find the 2 that work. But this shows here, if I use this algorithm, I use a recursive algorithm, kind of the way we described it, that we only have to do a total of 60 checks out of the 256. We only have to check 60 possible times, and then we can figure out when things are wrong. Because what happens is, think back to here, once we knew, like I say, if we knew this was wrong, like this doesn't work out, why would I need to continue on with anything more? All of those possibilities that would come after it, we can just scrap them right off the bat because there's no reason to, because this is false. Anything else adding on to that is just nonsense. So that is, so from a 4 queen standpoint, it's pretty easy to understand, pretty easy to look at. But from an 8 queen standpoint, or even more, right? Because this code that I have here for you guys in this video basically can handle any case. It's not the most, it's not the most efficient code ever, but it's code to show you the basics for what you're trying to accomplish. So for 8 queens, there are 92 different possible ways. I don't know exactly how many are mirror images of one another or whatever, but you kind of get the whole point here is that I put a queen here, and then I put a queen here, and I put a queen here, and so forth and so on. And we're going to try all the cases like we did before. But so like this, if I'm going to put a queen at location 0 and then at location 0, I don't have to do all of those extra works, 8 times 8 times 8 times 8 times 8 times 8 more possibilities, because I know that no matter what, we've already started on a bad condition. There's no reason to continue forward. Same with this. There's no reason to do all the work. But if I get to here and I go, yep, so far so good, and then I go, nope, 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 then yep, and because this works out, and then now I can continue on forward. So we're basically pushing and popping all this information onto and off of the vector. If you want to think of it almost like a stack. And so when it turns out, when I can add 8 things to it, I'll print out. Like when I can validate and go, yep, I've put 8 queens on the board, and the board is still in a valid state. Print out that solution. And that's what this is doing here. That's what it's doing. It's printing out the values for where to put all the queens for each of these 92 states where you can put this thing on the board. But basically, at any point where it says, oh, there's a failing, well, we fall back. We say, nope. Let's take this, like in this case again. If I'm tempting this and I say, nope, this doesn't work, we'll take it off the board and try again. And then you go, okay, that's legitimate. Or like this, if you even get down to here and you go, okay, I put one here and I put one here, and you go, nope, that's not right. And you go, well, put this one off, and then we're done here, so we got to come back and move this one down. So it tries all the possibilities, but it only tries the ones in which it knows it can at least make an effort and maybe find success. So that's the idea of what the algorithm is going to do here. So let's jump into some C++ code now. So there's quite a few functions, not too many, but enough functions that I have to tie this thing together. So the first thing you see here on the board, I'll cut this thing off, one day I'll get this right, is that I have a function that determines true or false. You give me a vector of integer values, and I will tell you if this thing, this vector, constitutes a legal board. And so, coming back, you can only put 1 queen on a column, right? So is presuming that each element holds a number value with where the queen is in that column, you will never put, because you can't put two values into the same element, I'll never have to worry about verticalness when it comes to the 3 different ways I have to check. Because I have to check vertical, I have to check horizontal, and I have to check diagonal. So in this case, I never have to worry. Look at the code here. I'm testing horizontally and diagonally, but I'm not ever testing when it comes to verticalness. And so that's a great first, so I don't have to do that work. So in this case, look at this here. I have a 0, a 3, and a 4. And I'm just like, how am I supposed to know? And so there's a presumption here that only the newest queen can pose an issue, because the way we're setting things up, right? We're adding queens to this, but as soon as I figure out that this isn't going to work, like I'm gonna stop. So like if this had 2 or more queens in it that were bad, that did not work together, this is not going to work out for us. This just presumes that everything up into it, but not including the final one. So like this algorithm will not work if I give you a 3, and a 4. And that's because, again, this would have been like when I was adding to this thing earlier, when I got to 3 and 3, it would have come up and say, nope, this isn't working out for me. So this doesn't test every possibility. This just tests the final one, the last one in the list against all the others. So this would have kicked out on us and said, nope, that's not legal. And so we would never have allowed ourselves to get to anything else past this. So coming back, so just to say, so it's saying that everything up to, like if I took this queen off the board, the last one here, if I took this queen off the board, everything else would be legal. But the question is, if I add this guy to it, if this, is this one allowed to be added without causing any problems? And you can see, obviously, the answer is no, but how do we prove that? Okay, so again, the horizontal check, that one's simple. So like I say, I'm testing the back element, which is the 4, because this is the last one against everything else. And so the horizontal check is easy. If any of the other elements have the same value as me, then I've proven that it's not legal, right? Or just because if this was like this here as a 3, and you go, nope, it can't possibly be because these 2 queens have the same value. They're at the same horizontal row level. So no, so that's the check there. So again, okay, so in this case, nope, horizontally everything, oops, sorry, change this to 4. Because this value is unique compared to all the others, we're good. So then now diagonal is just a little trickier, and that's because starting from this, the 4 location, if I work my way backwards, now I have to check location 3 and location 5, right? That's just how diagonal works. So I say I'm at 4 now, so +1 and -1 from the value I'm at. And if I moved over 2, right? If there was a queen here, then I would have to check 1, 2 up. 2 over means 2 up, right? Just basically a slope of 1. So every time I try to go one element over one more time, I have to go up and down one more time. So let's put this, let's put it like this instead, right? So let's see, this is a 2, this is a 0, this is a 4. And so it just comes out to, so I work my way backwards and I say, okay, now I'm going to check against 3 and 5, nothing there, because it's a 0. And then I'm going to say, well, why don't I check against 2 and 6? And I go, yep, the 2 is definitely a match. So then they are matching diagonally, so I'm going to return false. And that's what this diagonal test here is doing. You can see plus offset, minus offset, and if the values are identical, if the value of this guy, the value that I'm testing against is equal to the value of the back element, then yes, I have a diagonal check. So I say, again, vertically I never have to think. It's already done for me because of the way my algorithm is set up, my data structure is set up. Horizontally, just checking to see if any element shares the same value. And then diagonally, just checking as I'm going back, does it match up with the offset of everything? And so if I can go through those 2 checks or 3 checks and not find any single counterexample to this thing, then I have to presume that this thing is a legal construct and I have to return true. This doesn't mean that I did this right, like I did do it right, but just because I can't find a counterexample doesn't mean that I screwed up and there's no logical errors inside of here that I have to, that I don't have to worry about anything forevermore. Again, all of programming is how sure are you? How close to 100% sure are you? And I never give 100% because I'm 99.999% sure at this point, but there could be some tiny little thing that I didn't account for that will come and kick me in the butt later on. So that's the idea of the is legal portion of this. And so coming back to our description when I showed you how to do the 4x4, so we need that function, but now look at the n queens problem. If you've watched any of my other recursive videos, you see I have a public-facing function and a private-facing function. And so the public-facing function is easy. Tell me how many queens you want to put on n queens on an n by n size chessboard. What do you want it to be? And so I passed a 4 along earlier. I changed it to 8, and I could change it to 11 if I wanted to. Everything, of course, will run a little slower. But you can get up, there's all 2,680 possible solutions out of the thing. And you can imagine as the thing gets larger and larger, it gets slower and slower to find them all because it just gets more and more daunting for the computer to crunch all those numbers. And so just bringing it back to 8 by 8 again, you go, okay, I want to pass in 8. And so here's the cool part here. I love, my algorithm. Who doesn't love these kind of algorithms here? So what am I doing? I'm passing in, I want 8 queens, and I'm setting up a vector, and that's because this thing is going to be a reference, I have to create it ahead of time before I call the recursive function. I can't just create it inline inside of here, because at that point then it's a value type and the compiler is smart enough to kind of shut that down. So I just set up a v-size vector, I reserve however many elements I need, and then I start the process and just say, okay, there's 8, here's my vector, and in this case it's an empty vector to start, and I'm going to put, maybe I can do, maybe do this with 4 again, just to kind of, because 8 is going to get a little too daunting, right? So anyway, I want to do 4 queens, here we go, I want to do 4 queens using an empty vector to start. There's 4 queens I have to put on the board that still have to be put on the board to see if I can find anything legal, and I'm going to put a total of 4. This total is never going to change, but the number of queens I have to try to put on the board will as I continue forth with my algorithm. Okay, so that's the idea, and I need to pass this along because I'm not going to use it. I'm not using any globals, I'm not using anything like that, but I have to know how many are left and how many I'm trying to put total. So to make this work, I need these 3 pieces of information on the private side. So, okay, so the base case, one of the base cases here is what happens if I have 0 queens left to put on the board? Well, if that's the case, that means I did my job coming back. Remember, it was this one, this one, this one, and this one? So if I do all this work and I go, oh, there's 0 queens left to put on the board, done. And then what I do is I just print the vector out, because this would be 1, 3, 0, 2. Hey, I did it right. So 1, 3, 0, 2, and it'll print the 1, 3, 0, 2. And it does, right? Because that's, oops, I didn't change it to 4, didn't I? I thought in my head I did while I was talking about it, but I did not. So there's my 1, 3, 0, 2, and there's my 2, 0, 3, 1 that comes out of this. It just prints out the vector. Okay, so coming back, we can, it won't take too long to exhaust all the possibilities here. So what does this function do? I'm passing along, total left to place, there's always going to be 4, total to place, and then left to place is going to be 4 to start. So okay, so what am I going to do? I'm going to push a 0 onto my vector. So we'll use this as my vector right here. Okay, I push a 0 onto this guy, and then I say, okay, for I equals 0, I is less than total to place, which is 4. Try to put it, plus I, so my I value is going to be 0. And so what am I doing? I'm going to put into the back element the I value. So put a 0 in here. Okay, and that and it's weird, right? Because this does return a reference, so I can modify a reference with a value, and it's actually going to modify the vector, so it'll actually change the value to 0. And so it'll put basically, I'm saying, you never see this. This is just a visual representation of what this vector is representing. So now it says, hey, is this legal? And so it calls the function we talked about, and it goes, yes, it's legal, because there's no queen attacking that queen, right? Because it's just 1 queen on the board. That's perfectly fine. So if that's the case, it's legal in this situation. I'm going to call a recursive algorithm and say, now I want to put 3 more queens on the board, and I want, and out of the 4 that I have, send this vector, now that's not empty anymore, push that onto the stack. Or, let's call this out. So now, same thing goes before. Well, there's not 0 left to place, so it's done. Push a 0 onto the stack, put a queen at location 0, and then say, is it legal? And it says, nope, this is not legal. And so what happens is it doesn't call, because it's not legal, it does not call the recursive algorithm to continue forward and try to put more in there. So then what does it do? It comes back around and says, oh, now I is 1. Let's try I of 1. Let's put a queen here instead. And it says, nope, that's wrong because it's diagonal. So then it's like, how about 2? And I go, okay, we can try 2, because that comes off as legal. And so now what do? I can go in and recursively try to add another one. So now I'm going to go, there's still 2 left to go, nothing to do here, push a 0 onto the stack. And so try here and say, okay, try the 0. That is not allowed, so no recursiveness. Try to put 1 here, nope, that's not allowed. Try to put 1 here, nope, that's not allowed. Try to put 1 here, that's not allowed. So we've gone through this entire for loop, and we haven't found anything that we can recursively go through, so we fall through it because there's nothing more to check. And when we do that, we say, give me a pop back. So take this off the list and come on back. And then now this is the tricky part, remembering the recursiveness of this. We're coming back into another iteration of the n queens function, and we're still stuck at 2 here. So now my next option is, let's make this a 3. And start over and go, yep, that's legal, so I can try again. And then this says, oh, this is illegal. Nope. And you go, well, this is legal. Okay, that's good. So this is legal, so I can put a 1 here and say, let's try one more time. And you say, okay, you think you're onto something, right? And you're like, oh, let's put a 0 here, push a 0 on here, and try. Nope, 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 nope. So everything falls through. We got very close. We got 3 of the queens on there, but we didn't get all of them. So we fall through here. We pop this back. We say, okay, 1 didn't work. Well, how about 2? And you're like, okay, okay. So nope. So this, so this doesn't work because it's diagonal. Okay, so I don't have to worry about that. What if I tried to put it here? And you say the same thing goes. Nope, this doesn't work. So this falls through, and we work our way back. And so now there's no more to go here, 2 iterations back, because we've tried all the possible solutions. And so now this falls off. And we knew that there was nothing when you put 1 in the corner. There's nothing we can do about that. So now this becomes a 1. I keep pushing Q and 1s and stuff like that. But you see where this is going, right? So now I try again. Let's add a 0 to this and try all these possibilities. Nope, nope, nope. But we can put 1 here at the 3 location. And so now, cool. And you go, well, okay, put 1 here at the 0. Yep, that's still legal. Cool, we're onto something. Try the 0, can't do it. Try the 1, can't do it. Try the 2, I can do it. And so now when I get there, I go, okay, let's try n minus 1. So now we're gonna hit this thing, and so left to place. We've put 4 queens on the board. There's 4 spaces. There's nothing left to place. Play the music. We hit a solution. Print that vector out, my 1, 3, 0, 2. And then we're going to continue on. And this is because I hit this, and so it's going to keep going and try that. 1, 3, 0, 3, but it's going to fail. And then it's going to kick back and say, should I try this? And it says, nope, I don't need to try this because that's a failure. I don't need to try this because that's a failure. I don't need to try this because that's a failure. And then I don't need to try this because this is all done. And so you can, so I'm going to save you all the other stuff, but you can continue on through all the other possibilities here and say try 2. And remember, 2, 0, 3, 1 is a possible solution. So let's just do that one and then call it a day. And so okay, so now I'm at a 2. So push a 0 onto the stack and try it out. Say, okay, I can do that. So now try to push a 0 onto the stack again and then say, oh, that's not allowed. That's not allowed. That's not allowed, but this is at location 3. And so go, okay, now we'll try to add a 0 to this and go, okay, that's not allowed because there's that. But this is. So it prints because it found a solution. It's going to try to add 1, puts the 1 on there and tries to add 1 more and says, oh, there's nothing left to place, print it out. And so we know those are the only 2 solutions. So we don't have, so if you want to, again, the computer will keep trying. It'll say, oh, I don't have to can't do this, can't do that. And then this will fall down, and then this will try to move, but it says, oh, I can't put it here because this is diagonal, this is diagonal, this is diagonal. And so then this falls through, get rid of all this stuff, and now then the queen comes down here. I guess I wasn't going to do it, but whatever. And so now the 0, I could put 1 there. But then I can't put 1 here, can't put 1 here. I can put 1 here. And then can't put 1 here, can't put 1 here, can't put 1 here, can't put 1 here. So I come back, try to move her down. So I can't do it. So then I go, okay, well, how about I come back now and try this one out? Because that's legal. And it's like, can't put 1 here, can't put 1 here, can't put 1 here, can't put 1 here. So that I can't do anything more. Come back again, put a queen here and say, nope, that's not allowed. Can't put a queen here. That's not allowed. And then I fall through, and my recursiveness just completely unravels, and everything is complete. And the 2 solutions that we discussed comes up for 1, 3, 0, and 2. So say I rushed through this all, but we only truly did 60 validation checks. We could have done all of them, every single one. We could have just kept randomly choosing. But at the end of the day, Out of those 256 possibilities, we only needed to check 60 of them. So coming back to the 8x8 method, and there's nothing different between 4x4, 5x5, and so forth and so on. The only difference is the size of the board and the number of calculations that have to go down for you to figure out, yes, this is good, this is not good, and all of that. Because, like I said, if you choose, this is 8, there's 8 choices and 8 columns, 8 to the 8th power. That's actually 4.29 billion. That's int sized. So there's 4.29 billion different possible ways you could test this, but we found the 92 solutions only testing 15,720 of them. So we reduced a huge problem down into a very tiny one and got all the same solutions, and we've proven we do not need to worry about all those extra cases. So that is the essence of how the n-queens problem works. And so you can look up, like Knight's Tour. There's all, a bunch of other different recursive problems that kind of solve different problems in the same way. You just keep going until you hit a dead end, and then you work your way back, and then you keep on going. And so a homework assignment, which those of you in my class will have to deal with, is a Sudoku solver. A Sudoku solver is, Sudoku is one of those games you put 1 through 9 in each row, column, and square. But like, if I gave you a problem and you go solve it, could you do it? And so logically, it would take us a long time to think it out. But if the computer can brute force it and take that configuration and just basically try out all, like a big maze, just try out all the different ways and find the one way that isn't a dead end, and then go, here's the solution. Because we found 2 ways in our 4x4, we find 92 ways in our 8x8, and when a Sudoku puzzle comes in, it should just be one solution with the configuration that they've given you. Okay, so let's see, n-queens, there's my functionality for that, and just so you can see it, so you can type it out. There is my functionality for my isLegal function, and then there's my functionality for my print vector. So, I mean, I've described the whole thing in however 20-something minutes, and that's it. So my email address, swardb@cod.edu, that's where you can get a hold of me if you have any questions, or you can send a question here through the YouTube channel. Thanks for sticking up with me as always, and thanks and have a great day.